how do we implement Bayesian optimization for our purposes, which is in hyperparameter optimization? And I'm going to ask all the questions that practitioners would ask. And as a practitioner, I've made a note of what are the rules of thumbs so that you can take those rules of thumbs as is and develop from there rather than stabbing with a blank book. Okay, so let's start. So our agendas are, obviously, we're continuing where we left off in that video. The first question we'll ask is, which surrogate model is right for us? Okay, we know that the surrogacy is the idea with which approximating the black box function is happening. In our case, approximating or trying to kind of find this right solution within this hyperparameter space is going to happen based on this surrogate model. So first question we have to ask is, which is the right surrogate model? Okay, so we'll see a bunch of surrogate models and know which one to use. Second one, we also must ask the question, if we have a bunch of hyperparameters, a bunch of features for which hyperparameters need to be searched, which are the ones that are really important for our solution space? You know, you may have done importance of a feature using, let's say, a random forest or some tree model, correct? But there is a different way with which the Bayesian search will now teach us of how to find important parameters in the solution space as it finds them, okay? So that is a very good reflection that we will also get. Third one, obviously Bayesian search is very powerful, but can we speed it up more is a question we'll ask, and we'll do too. Fourth, how are people going to implement it? Because earlier we saw a very small snippet where I said, at the minimum, replace your grid search CV with a Bayesian search CV. And it was just one line of code I showed you. But now I'm going to undo that. I'm going to show you more pieces, which is how practitioners do it. Okay. And then finally, obviously, we'll also learn how to visualize this optimization space. And for us to say the storytelling on that visualization is important so that we know that we have a concrete hyperparameter on which we are locking down, rather than be very, black box driven. Okay, so we have to know how to understand this visualization. So let's get started. Which surrogate model is right for us? That is the first question. So there are a bunch of surrogate models. First one is Gaussian processes. This is the maths I covered in that video. Because the math is simpler, I've covered the Gaussian process math in that video. Even though it may look elaborate, it is actually simple. If you see the video a couple of times, it's going to be in your belt. Gaussian processes are good, are usually the one that we will usually pick. But we have to know a few things. The Gaussian process is going to expect that our overall function is kind of smooth and predictable. Okay? So in our context, when we are talking about our tabular data or images and stuff, this is acceptable assumption. Okay? Because we are not going to see unnecessary jumps. But when it comes to NLP, we can get challenged. So just keep that in mind. Okay? A lot of your tabular data problems, a lot of your image problems does have that smooth and predictable response. Therefore, Bayesian could use Gaussian process, which is by default. And one more thing to note always about this is that it may not find the right minimum for you, but we can resolve this problem by looking at the plots of what it is finding and try to kind of really find if we found the right minimum, or should we run more for the Bayesian search to find the right minimum. Okay, so this is something to keep in mind. The Gaussian processes are usually not recommended for very complex search processes. So if it is a small neural nets, that is okay. But when we have a deep neural net, and when you're talking about large language models and stuff, Bayesian itself is not directly used. Okay, there is something else that's going to be used. I'll make a note of that as we come through this. But just keep in mind that Gaussian processes are very powerful for your standard classical machine learning problems. There is one more optimizer that also works very well on the classical tree models, which is called the forest Bayesian optimizer. This was tuned from the Gaussian to cater for the forest kind of a problem, which is all this this random forest kind of a tree models. And there is one more, which was again tuned for the gradient boosted trees, which is called the gradient boosted tree Bayesian optimizer. Okay. And whichever surrogate model you want to try them, no problem. But the final choice of which one you will use, you will be making it based on what is called as convergence chart. Okay, you will quantify them. You will look at how my Gaussian performed, how my Bayesian performed, how my gradient boosted optimizers performed. Optimizers means the surrogate model performed, and then decide based on that convergence chart. I cover that convergence chart in a couple of minutes. Okay. And one more rule of thumb that I observe: if your data is very large, 100K plus, 200K plus, then it is better that you random sample a certain percent of your data, bring it back in as you look into convergence chart. Otherwise, the convergence chart itself will become a very, very complex for us to nail down, which is the actual surrogate model for you to finalize. Okay? Very good. So are we all good when in this particular slide, what we are talking? So surrogate models also called the optimizer. So that's just a terminology. Let's now come. Let's make some assumptions, start visualizing the convergence chart. Let's assume that we are running a random search. Now I'm gone back to random search, okay? And I'm storing the results in this particular variable, RS solutions, okay? I'm also running Bayesian Gaussian optimizer, and then storing the results in GP solutions. Okay, so RS solutions is my random search. GP solution is my Gaussian process search. Very good. And I'm also going to run a random forest specific Bayesian and store the results in RF solution. I'll show you how to store these, but right now just know that I have done that work. Extra trees optimizer. So I have taken all the 4 available optimization techniques for surrogate modeling, and I'm storing them each in one particular variable. Okay. Later, obviously, in the video, I'm going to show you step by step how to set up the code and run all this. But now let's look at convergence chart. How to choose the surrogate model. Okay. So this is kind of one sample convergence chart that I have, where it is showing me random search performance, Gaussian process performance, which is here, random forest optimizer. Yeah, this is not random forest classifier. Random forest optimizer performance and extra trees performance. What are these 2 axes? One is what sort of a minimum function am I getting? So this is kind of, think of it like the minimum point I want to achieve. Okay, so this, the lowest one I want to see, number of calls I have to make, meaning number of steps I have to run before I got to the lowest point. Okay, so now that X and Y are clear, now what is worth seeing is here. See here, around about this 17 sort of a figure, the Gaussian process came to this kind of a low value. It is not the lowest of everybody else, but it is the most simplest method, and it got there very, very fast just with 17 steps. The next one is extra trees. About 22 steps, it gets me a low, but it also gets me quite low from that end. And what is worth seeing here is comparing them. How was this point, when was this point reached by others? Did it reach at the same time? No. So the best in this, which got me the fastest result right now, is Gaussian process. But that is not the lowest point. It got me a good result, but it is not the lowest point. So keep that in mind. Next, let's come back to random forest optimizer. It took more time. It took more steps even to reach this level. But it kept going, and it got me this low. So thus, it is getting me a much, much more nicer solution space in the minima space, even though it took almost 2 times the step size. So instead of 17, now I have 34, something like that. And I got pretty low values compared to what I got from Gaussian process. Okay. And what did the random search do? Random search tried various things. It didn't even come this far. See here, Gaussian got it in 17 steps. Where is it getting? Almost about 35 steps. It's not even breached there. This was probably the 35th step. Then somewhere down here, it became a little lucky and then goes in the straight line. Okay. So what is the message from here? Message is, for us to decide which model, we obviously must know where our minimas are achieved, how many steps afterwards it's achieved, and what is acceptable for us. Do we want to always go to the random forest and spend 34 iterations as we get to the most minimum data point? Or are we okay to kind of like settle for something a little bit bigger, but we got there much smarter, much faster? Okay. So that is something we need to keep in mind. And what sort of a code is needed to write this? The skopts package has this plots function, and it helps you plot the convergence plot. So it's one line call. I will show you how I initiated RS solutions and all later in the slides, but right now, as long as I have initiated the RS solution, GP solution, all these solutions, then this chart is just one line code. Okay. Next question we have to ask is, are we doing this search in a smart way? How smart is this search? Can we quantify that, right? So let's see that. I'm going to again make some assumptions of variables and stuff and show you some charts how to figure out if we are smartly searching or not. Okay. So we have run random search. This is not Bayesian search. It's random search and store the results in R solutions. We have run Bayesian search, store them into GP solution. Okay. Only 2 variables here. Let us see the visualization. How good is my optimizer, search optimizer? First is my random search. Okay. What I have here is a random search for 2 variables only. So it basically tried various values for the first feature, second feature, and it is showing me here where it found the minima and where and all it tried randomly trying to find the minima. It tried various points as it tried. Let's see what the Bayesian search did. Bayesian search just narrowed down and searched only a certain segment in the feature 1 and certain segment in feature 2. And it got me a minima out here. It did not go and search randomly all over the place, but rather it was always focused on this one zone, but it was trying to kind of like move forward in a certain way. Okay. So these darker dots tell me that I was getting better and better results. And the lighter greens maybe less of a result. Okay. So this shows the importance of being focused in that direction where the solution is, which the Bayesian optimizer gives us compared to a random search. And how am I plotting this? I'm using again skops.plots function where I have this function called plot evaluations. I'm calling plot evaluations for both my variables, which have been run for random search. One is run for Bayesian search. Yeah. Most important thing, take away from here is whenever we are looking at these evaluation plots, look for clusters. Look if there is a cluster formation around, whether it is whichever model you're going to see, whether you're going to, this time we have seen the Gaussian processes of the Bayesian search. What if you are also looking at extra trees optimizer of the Bayesian search? Then irrespective, when you're comparing them, look for clusters, and if things are moving within a cluster to the convergence point. That is a key takeaway. Okay. Next important thing we are going to be asking is this, which is, how do I know which hyperparameter space is really driving my overall minimization result, which is how important some of my hyperparameters are, right? We know the feature importance from the tree models, but then the underlying hyperparameter value importance is something that we want to learn, which we can learn using something called as objective plots. Okay, again, part of the Bayesian optimization package. So if you do a plot, I'll show you the code for plotting this, that you will get something like this for a 2 feature. Okay. We also know that earlier we saw how this clustering was happening, and then eventually it came to my minima point. That is all good. But then it has tried a few values and saw how my minima, how some of those values were moving the overall objective function to the minima. Okay. And that is what these 2 charts are indicating. Okay. The most simplest way to read it is when these charts have significant movement, irrespective of the direction, it tells me that it is moving me from an objective score perspective. However, if I see a lot of flat lines, it tells me I am ineffective, or at least this particular hyperparameter, this particular feature is ineffective in this space to give an impact into my objective function. Okay. Yep. So I repeat, when you see these movements, that means it is impacting my objective function score and thus motivating the system to go more and more to the minima. All right. Whereas when we have parallel straight lines, these x values are ineffective in finding the minima. So here and all, these values are ineffective. Whereas if you see here, up to this was effective, but after this was not effective. Again here, not so effective. Okay, so that is important to know. If you have a particular solution, let's say GP solutions for the Gaussian processes, then plot objective. It's the only function we need to call to do this. Then we also must ask this question: when should we not use a Bayesian optimization? It is a powerful tool, but knowing when not to use is also an important thing as a practitioner. First, when hyperparameters are in excess of 16 plus, then don't use, or it is not recommended to use Bayesian optimization. Okay. In such cases, people recommend you go to a random search or do something called as a tree parser estimator. So this is another branch of optimization techniques that has its own math, again, underlying principles of how it solves the problem. But tree parser estimation is probably the place for you to go when it's more than 16. Okay, random search. If you don't have any other option, then you do with random search. Otherwise, go with tree parser estimator because it's sophisticated. It can solve various other problems, including neural net related problems or finding solutions in neural nets. The second place where we don't recommend using a Bayesian optimization is when your search space is highly nonlinear. So when you're in deep neural nets, the space is very nonlinear, in which case people have seen that Bayes optimization does have certain disadvantage. It's not really finding me the minima we want it to find. It's taking more longer to push it to find the minima. That is exactly what is happening. So people don't recommend that when you have a very deep network. But if it's a shallow network, if it is some sort of a tabular data for which you're finding it, Bayesian optimization shouldn't have a problem. Okay. And who recommended this 16? I have always been curious, and I found that it is Google's recommendation based on some of the research papers and tests that they did. Very good. So if you want to learn more on, let's say, tree parser estimator, which is again another branch of optimization, do ping me and message me, and we'll do a session on that. The next practitioner's question we'll ask is how to speed up this search. We know it is faster than random search in finding a good solution, but is there a way we can make this more faster, right? So that is important. There are a few guidelines we are going to be going through, okay? I'll go through this guideline. First itself, I'll tell you, don't worry, you'll see this list. We are going to implement the pieces in this list later when I show you the code, okay? So just get the gist of what we are using to speed up the Bayesian optimization. Number one, apply early stopping. This is a very important technique. We are going to be applying early stopping on what? Both the machine learning model and the objective function using some validation strategy. Now, that could be cross-validation strategy, like, you know, what cross-validation strategies we have seen? K-fold, right? So that's very popular. Or it could be something else, like cascaded K-fold cross-validation strategy that I have earlier spoken in one of our masterclasses, right? So right now, let us move on. So the key thing is we should put early stopping both on machine learning model and also on the validation strategy. That is the key idea. Do not hyperparameter tune the number of estimators for tree-based models. This is something that we may accidentally do based on some earlier pieces of code that is there in the code base or some academic code coming from GitHub. But watch out that we are not going to figure out the number of estimators for tree-based model. Let's not do that, because that is a separate exercise compared to finding the value for those parameters. Okay. So what would be an example? Number of estimators means what? Number of estimation, n estimators in XGBoost, dbtree, forest models. Don't use this. Don't bring this n estimator in as your hyperparameter optimization. Figure that out as a separate exercise when you do the model selection. That is what we are saying. Or alternatively, you can set up the n estimator to a very, very large value. I've just set it up here, 25,000. You could set it to 100K, whatever those particular large numbers are, and then just do early stopping. Okay. Though this is not recommended, if you really have to do it, take this approach. Use convergence charts to decide on your surrogate model. Don't forget the fact that there are multiple surrogate optimizers available. You are better off with one of those optimizers for your own particular model or a problem space you're dealing with. Therefore, even though the default is Gaussian process, no need to always take the default. Use it, it is good, but try surrogate models and figure out what works best for you. Another thing is with the acquisition function. Acquisition function is the smart algorithm or machinery for it to pick the next spot or the next parameter space to try. So for that, again, don't fix it to one thing. Rather, there are some probabilistic based methods that I will show you in the source code. Use them so that it can automatically pick the best method that works for your problem. Okay? Very good. And then one more thing that you probably are already doing, if not, you should do, is you should have some valid starting points. Just don't do, just a random starting point, because the random starting point could be the worst place to start, which means it'll take more time for the Bayesian optimization to come to the path where it should come to. It doesn't impact it so much, but it does have a say. Therefore, usually what people do is they will do a lightweight random search, just a very quick random search, which will run in, let's say, a minute, find a bunch of prior values, which can give you some minima, and push that back into the Bayesian. Okay? Very good. And to make life easy, the implementation I will show you, I factored all this in, and I'm going to show you the code for it step by step. Very good. So far, so good. What we are going to do in the implementation is we are not going to do this easy one-line replace. Even though if you want to try that for the first time, no problem, go ahead and do it, because your grid search CV can be replaced with one-line code by Bayesian search CV. That is what I told you earlier in that video. But when it comes to really implementing them with a proper pipeline and stuff, which is what we're going to see as we continue, this is not what we're going to be doing. We're going to do a little bit more elaborate work. All right?